Hey guys, so you should have already finished your online virtual Glencoe solubility lab. Please do that before you start taking notes, pages 3.5 through 7. So we're going to start here in the middle of page 3, looking at a solubility graph of per 100 grams of water versus temperature. So when we're looking at our axes, we have temperature here on the x-axis, and we have the solubility, grams per 100 grams of water. So if we look in general, all of our lines are going up. So as temperature increases, the solubility is increasing for the majority of our compounds. There are a couple of exceptions. Let's look at what sodium chloride does. That stays pretty flat. So if you're trying to dissolve salt, heating up the solution doesn't really help. And we actually see an opposite trend. If you look at YbSO4, ytterbium sulfate, it actually decreases its solubility as temperature increases. So we're going to go through and answer some of these graph questions. Describe what happens to the solubility of KNO3 potassium nitrate as temperature increases. So here's KNO3. It increases. Is that a linear increase? It looks to me it's almost like an exponential increase. So in general, the solubility goes up, and it looks like it could be exponentially. Which substance shows a decrease in solubility? So which one has a negative slope? That's going to be the ytterbium 3 sulfate. So YB2SO4 3. Question 3. Suppose you added some NaCl, some sodium chloride, to a saturated solution of NaCl and warmed it to 40 degrees Celsius. So let's say we're somewhere below 40, maybe we're at 20, and I added more and I warmed it to 40. What would happen to the added NaCl? Nothing. It would not dissolve. So it would not dissolve. It would sit at the bottom of the beaker because sodium chloride solubility does not increase the temperature. However, if we added KNO3, let's look at that line. If you went from 20 to 40, it would definitely dissolve. It would go into the solution because of its solubility curve. So what three pieces of information can you use or derive from this graph? So we could say that NaCl's solubility is pretty much constant. Most increase when the temperature increases, the solubility increases when temperature increases, except the ytterbium 3 sulfate. So except the ytterbium 3 sulfate actually goes down as temperature goes up. So when you make sure you take some time and look at that graph, you could definitely see some quiz questions about that solubility chart. Okay, let's classify each point as saturated, unsaturated, or supersaturated. So if we have 40 grams of potassium bromide at 60 degrees Celsius, let's find 60 degrees. We're going to find 40 grams. Let's go and find that intersection. And if we are on the line, we are saturated. If we are below, we are unsaturated. And if we are above, we are supersaturated. So let's find where potassium bromide is. Here is KBr. So at 40 degrees, it can hold about 90 grams. If there's only 40 grams, that is going to be unsaturated. Now let's look at 100 grams of sodium nitrate. So here is 100 grams. Here is 40 degrees Celsius. Here's my intersection right here. And they said sodium nitrate. So where's my sodium nitrate line? Right here. I am just above that line. So I would be super saturated. There's too much. Okay, and let's finish up with 100 grams of sodium nitrate at 45 degrees Celsius. So here's 45. Now I am right on that line. So that is perfectly saturated. Now expect to see some quiz questions like that. So remember, if we are over the line, that means that we are super saturated. If we are on the line, we are perfectly saturated. And if you are below the line, you are unsaturated. You could add more. If you start with 50 grams of potassium bromine at 80 degrees Celsius, how much more potassium bromine can be added to make a saturated solution? So 100 grams, 45 degrees Celsius, that puts us right here. If we're looking at potassium bromine, its saturation point would be at 80 grams. So let's see. If we have 50 grams, how much, oh, I said that backwards. Okay, if you start with 50 grams at 80 degrees, how much more can you add? So here is my 50, and we want to go up to 80. So 50 plus what gives me 80? We could add 30 more grams. If we put 40 grams of ammonium chloride into 100 grams of water, at what temperature will it all dissolve? So we're going to be looking for 40 grams, and what temperature would it all dissolve? So 40 grams for ammonium chloride. So go to your chart, 40 grams ammonium chloride. We're looking for when that blue line intersects. I'm going to have to erase some of the lines I've drawn here so we can see more clearly. So where does ammonium chloride intersect 40? It's looking like it's going to be right here at 30 degrees Celsius. That's going to be 30 degrees Celsius. How much water will it take to dissolve 160 grams of sodium nitrate at 10 degrees Celsius? So 10 degrees Celsius is right here. At 10 degrees Celsius, sodium nitrate can dissolve 80 grams. So at 10 degrees, it can dissolve 80 grams. 100 grams can dissolve 80. So how many grams would I need to dissolve 160? You would need 2 times as much. So that would be 200 grams of water. So that logic is pretty straightforward. If 100 grams dissolves 80, twice as much would dissolve twice as much. And how much water would it take to dissolve 100 grams of sodium nitrate at 10 degrees Celsius? So here we're going to have to do a little bit of conversion. You can either do some cross multiplying and dividing, or you can set up however you'd really like. So I know that I can dissolve 80 grams in 100 grams. So I'm asking 100 grams will dissolve in how many grams of water? So how do I solve for question mark? I would cross multiply and divide. So you'd have 100 times 100 equals 80 times question mark. How do I isolate for question mark? Divide each side by 80. And when you do that, let's see, take your calculator, 100 times 100, and then divide by 80. You should get 125 grams of water. Make sure you pause and check that math and make sure you get the same thing. Okay, let's turn to the next page. So page 4. Now I'm going to introduce some of the real chemistry you'd be doing in lab. We can define and calculate the molarity of a solution. We're going to be talking about concentrations of solutions. You have some experience with this. Think about if you're making Kool-Aid or Crystal Light or like mix your own Gatorade or Powerade, you can get the perfect consistency for yourself. If you follow the package directions, it probably tastes normal. If you add extra powder in, it probably tastes really intense. And if you don't put quite enough in, it probably tastes kind of diluted and watery. So you already know that concentration is a measure of the amount of solute in a given amount of solvent. If it's dilute, there's not very much solute in the solution. If it's concentrated, there is a lot of solute in the solution. Here are some units you could see. You could see ppm. ppm means parts per million. You'll see some pollution reports about parts per million. You might see some drug facts about parts per million. Molality, you might see on your take-home fudge lab. We won't use that too much. You can see it in AP Chem. We're going to be talking about molarity. So what is molarity? The formula is moles per liter. So we're going to kind of equalize everything by converting anything that's in grams to moles and dividing it by your base unit for volume, which is liters. So here is your algebra equation. Now, if you like using the triangle, molarity, capital M, is equal to moles per liter. So moles per liter. And just FYI, a lot of times we're going to abbreviate moles as N. It'd be confusing if we said M, so they've picked N. So molarity is N over L. So capital M is molarity equals my number of moles per liter. I'm going to do a demo with some examples in class, but we'll go through and kind of solve the math. So if the molarity is 1, that means that there's exactly 1 mole of solute in 1 liter of solution. So if I gave you a 2 molar solution, how many moles of solute do you think there would be? You're right, it's going to be 2. So there's 2 moles of solute over 1 liter of solution. And then if it was a 0.5 molar solution, what would that be? Well, that's going to be 0.5 or a half of a mole over 1 liter of solution. Okay, so let's look at a particle model. So let's take a second and pause real quick